Hello! In this video, we are going to prove the following theorem. For all integers a and b, a times b is an integer. Now in this series, we are using a list of 10 axioms for the real number system, and I'll leave that list of axioms in the description below. Now in this video, we are going to be using axiom 1, which is just the commutative law, and we're also going to be using the following 3 preliminary results. We have for all real numbers x times 0 is equal to 0. For all real numbers a and b, the negative of a times b is equal to a times the negative of b, which is equal to the negative of a times b. And we have for all real numbers a and b, the negative of a times the negative of b is equal to a times b. Now in our real number system, the real numbers are equipped with a subset called the set of positive real numbers, and it's denoted as r+. And using the set of positive real numbers, we defined the greater than relation and the less than relation. And importantly, we proved the trichotomy law, which tells us, given any two real numbers a and b, we have a is greater than b, a is equal to b, or a is less than b. So then, where do the integers come into play? Well, in our real number system, we defined the positive integers as a subset of the real numbers. And we have proven that for all positive integers a and b, a times b is a positive integer. And also, we have defined the negative integers as follows. We define the negative integers as the set of all real numbers n, such that negative n is a positive integer. And also, we defined the integers as the union of the positive integers, 0 and the negative integers. Okay, so now let's get into proving this theorem. To start the proof, let's first give ourselves two arbitrary integers a and b. From here, the whole goal is to show that a times b is an integer. And we're going to show this by splitting this up into several cases. One possibility is that both a and b are positive integers. Now, if a and b are positive integers, well, since the positive integers is closed under multiplication, we have that a times b is a positive integer, and the positive integers is a subset of the integers. So this tells us that a times b is an integer. So we're done. Another possibility is that both a and b are negative integers. If this happens, well, by definition of the negative integers, this tells us that negative a is a positive integer and negative b is a positive integer. So then, since the positive integers is closed under multiplication, we have negative a times negative b is a positive integer. But according to this result, negative a times negative b is equal to a times b. So this tells us a times b is a positive integer. And the positive integers is a subset of the integers, so this tells us that a times b is an integer. So we're done. Another possibility is that a is equal to 0. If a is equal to 0, then a times b is equal to 0 times b. But then by axiom 1, the commutative law, 0 times b is equal to b times 0. But then by this result, b times 0 is equal to 0. And 0 is an integer. So this tells us that a times b is an integer. So we're done. Another possibility is that b is equal to 0. Now if b is equal to 0, then a times b is equal to a times 0. But then by this result, a times 0 is equal to 0. And 0 is an integer. So this tells us a times b is an integer. So we're done. So at this point, we have considered 4 possibilities. So then what possibilities are left? Well, if we think about all the different possibilities we could have, well, we could have a is a positive integer and b belongs to any one of these sets. We could have a is equal to 0 and b belongs to any one of these sets. Or we could have a is a negative integer and b belongs to any one of these sets. So we have a total of 9 possibilities. But we've already considered the case that both a and b are positive integers. We've already considered the case where both a and b are negative integers. We've considered the case a is equal to 0. And we consider the case b is equal to 0. So this leaves us with two possibilities. We could have a is a positive integer and b is a negative integer, or we could have a is a negative integer and b is a positive integer. Let's first start with the case a is a positive integer and b is a negative integer. Now in this case, since b is a negative integer, well, by definition of the negative integers, this means negative b is a positive integer. So then, since a is a positive integer and negative b is a positive integer, well, using the fact that the positive integers is closed under multiplication, we have that a times negative b is a positive integer. But according to this result, a times the negative of b is equal to negative of a times b. So this shows that the negative of a times b is a positive integer. But then, by definition of the negative integers, since the negative of a times b is a positive integer, that tells us a times b is a negative integer. And the negative integers is a subset of the integers. So this tells us a times b is an integer. So we're done. And now let's consider our final possibility, which is if a is a negative integer and b is a positive integer. If this happens, well, since a is a negative integer, well, then by definition of the negative integers, this tells us negative a is a positive integer. So then, using the fact that the positive integers is closed under multiplication, we have negative a times b is a positive integer. But according to this result again, negative a times b is equal to the negative of a times b. So the negative of a times b is a positive integer. So by definition of the negative integers, that tells us a times b is a negative integer. And the negative integers is a subset of the integers, so this tells us a times b is an integer. So we're done. So we have considered all possibilities of a and b. So this shows if a and b are any two integers, then no matter what, we have a times b is an integer. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.